to be a 2-pager with 7 questions in it. And this is what I like to call a thermodynamic analysis. And what I mean by that is we're going to calculate delta S. We're going to think about whether or not that is driven to be spontaneous. We're going to calculate delta H, think about its spontaneity, calculate delta G, etc., etc. So we're going to calculate all the possible values and see what happens. So this one is combustion of hydrogen. Hydrogen plus oxygen goes to H2O gas. I need my table. And all of these reactions that you'll see on the homework were built to be part of this table. It says combustion of hydrogen. Let's see, this is entropy. So we'll look up our entropy values for hydrogen, 130.7. For oxygen, 205.2. And for H2O gas, 188.8. And this time, to calculate delta S naught of reaction, it's actually going to be products times coefficients. So, well, let's just do 2 times 188.8 minus reactants times coefficient. So it's going to be 2 times 130.7 plus 205.2. And we will not be surprised when this is negative because we have 3 moles of gas going to 2 moles of gas. So that's going to be going to a less dispersed state for matter, which will mean that entropy will be negative. Let's multiply it out. 2 times 188.8 minus minus 89 joules per mole Kelvin. Now, based on this number, the next question we're going to ask is, based on your answer for the change in entropy, this reaction is driven to be spontaneous based on the change in entropy? Is not. And this one is not driven to be spontaneous because entropy is negative. And the way this works is if entropy is positive, that will tend to make it spontaneous, and we would say the other answer. But when entropy is negative, so delta S naught reaction less than 0 is not driven to be spontaneous. Any questions about what I've done so far? Okay. Well, from here it just gets, we just repeat, rinse and repeat, if you will, except now we're going to do it for delta H of formation. And we look up the delta H values. Now hydrogen has delta H 0. Oxygen has delta H 0 as well. These are the lowest energy forms, or the lowest enthalpy forms of these elements. So mathematically not too bad for this part. And then H2O gas minus 241.8. So mathematically it's just going to be 2 times this product minus the reactants, which are zeros. I get minus 483.6. And that's in kilojoules per mole, which is negative. So for the change in enthalpy, This is exothermic. Exothermic reactions tend to be spontaneous. So it is driven to be spontaneous based on the change in enthalpy. Keep going. And there is actually one of these on your third exam. So it's on the homework, it's on the exam. We're not surprised by that. But we do this one more time. This time using delta H values, or sorry, delta G values. And for oxygen, you'll notice that delta H and delta G are both 0. That will always be the case. C nitrogen, same thing. C hydrogen, same thing. So mathematically, not too bad so far. Looking up my H2O gas, minus 228.6. And now our delta, I keep doing that, I'm sorry. Delta G naught formation goes here. I'm calculating delta G naught reaction. And it equals 2 times this number minus 457.2. So, you know it's coming, or you will by the end of this homework. Based on your answer for the change in free energy under standard conditions from the previous question, is this reaction spontaneous? Delta G is negative. Yes, this reaction is spontaneous. That's the whole point of delta G. That's the whole point of the change in free energy, is to tell us whether a process is spontaneous or not. Now, based on your work from previous related problems, and it could say 1 through 6 here, what is the temperature in Kelvin at which this reaction changes from spontaneous to non-spontaneous? And let's see. So before I solve this, we know that delta S is less than 0, which tends to be non-spontaneous. And I will call it just non-spon. We have delta H less than 0, which tends to be spontaneous. And so we have this sort of two trends that are opposite to each other. Whenever that is the case, there will be a temperature at which it goes from spontaneous to non-spontaneous. And the way that you solve for that is by plugging into this equation, delta G equals delta H minus T delta S, with your values. And if you'll remember when we did delta H way back in the day, literally weeks ago, we said that we were not too worried about the naught symbols because we are going, and well, we used delta H at temperatures other than standard state, and we're going to let temperature be different than 298 Kelvin again. So here's what we're going to do. I'm going to put a naught on here, reaction, reaction, not reaction, even though T will not equal 298 Kelvin. And hopefully that's okay. And we'll use these values to come up with our temperature. And here's what this looks like. So the temperature at which this reaction changes from spontaneous to non-spontaneous will be the temperature at which delta G equals 0. And we haven't talked about it as we've gone over today's homework, but in the lecture outlines, when delta G equals 0, that is when the reaction, and we're about to talk about this anyway, is at equilibrium for reaction. And it's also when the reaction changes from spontaneous to non-spontaneous. So what we're going to do is we're going to plug in all our values. We're going to plug in delta G equals 0 and solve for temperature. So to solve, we're going to say delta G equals 0, delta H equals minus 483.6 kilojoules per mole. I always put everything in joules. And my S value, my delta S value was 89 joules per mole Kelvin, negative. Like so. And now I have two minuses make a plus. I take the 483,600 over to the other side. And I solve for my T by dividing both sides by 89. And I get that temperature equals 5,434 Kelvin as the temperature at which this reaction changes from spontaneous to non-spontaneous. So we don't have to worry about this reaction changing from spontaneous to non-spontaneous at any temperature that we're used to. But if you were studying conditions in space, say, or in stars, you might want to think about whether or not this reaction would really be spontaneous. Okay. That was a long problem. Any questions about it?